Welcome back. Today we're going to be discussing the topic of what is known as the exponent laws. Now, exponent laws are a unique phenomena that arises in the topic of algebra due to numbers multiplying with themselves in interesting ways. Now, what's somewhat intriguing is the fact that a number multiplying with itself is not necessarily very interesting at all. We know that the definition of an exponent is that whenever you raise a number to a power, such as a to the power of n, so when I write a to the side, to the left, and I have a small n, that means a to the power of n, and it just means that you're multiplying a with itself in times. All right, that was the basic definition of an exponent. So this is just the definition of exponentiation, right? And we learned that probably in the 6th, maybe the 5th grade. But what's kind of interesting is that when you multiply a number with itself, just from this single definition and a couple of other properties, such as the properties of fractions or the inverse law, you can actually start to create a number of rules that must certainly be true for specific exponents. So for example, say we take 2 raised to the power of 6. 2 raised to the power of 6 is just simply 2 multiplied with itself 6 times. So I've got 2 times 2 times 2 times 2 times 2 times 2. And what we can do if we start to apply the associative law is we can start to segment off these calculations. And we learned earlier in this year that if I was to, say, insert parentheses around, say, the first two 2's, and if I inserted a parentheses around the last 2 2's, by the definition of exponentiation, because I have 2 multiplied by itself 2 times, I can rewrite that as 2 squared. And by the definition of exponentiation, I may rewrite 2 multiplied by itself 4 times as 2 raised to the 4th. So now I have the following relationship. I can say, without equivocation, without any level of uncertainty, that 2 raised to the 6th power is the same thing as 2 to the 2nd times 2 to the 4th. All right, but let's go back to 2 to the 6th power. Let's back up a little bit. Let's just play around with the associative law. Let me move my sequence of parentheses, because that's really what the associative law says that we can do. And if I move my sequence of parentheses to, say, multiply the first 3 sets of 2's together, and then I'm going to multiply the last set of 2's together, then what we can say is that, well, 2 times itself 3 times is 2 to the 3rd, and 2 times itself 3 times is, again, 2 to the 3rd. So now I could say that 2 to the 6th is the same thing as 2 raised to the 3 times 2 raised to the 3rd power. All right, let's play around with this idea a little bit more. Of course, I could shift my parentheses again, and I get 2 to the 4th times 2 to the 2nd, and that's really what we had originally. And I can shift my parentheses around one more time. Maybe I'll multiply the first 5 2's in sequence and then multiply it with the last 2. Of course, 2 by itself is just 2 raised to the power of 1. So one of the rules that a lot of students will remember from their middle school courses is this idea that when you start to multiply a sequence of numbers with itself in series, it seems as though the exponents add. If we, for example, just look at this relationship between the exponent 6 and the exponents 2 and 4, and we ask ourselves, how is 6, say, related to 2 and the number 4? Or we look to this next row, and I see that 6 is related somehow to the exponents 3 and 3. Okay, and I look to this last row and I see that 6 is related to the exponents 5 and 1. And I ask myself, what could this relationship be? What goes in the box? How can I relate 2 and 4 to 6, 3 and 3 to 6, 5 and 1 to 6, if I was to just consider the basic operations of addition, subtraction, multiplication, and division? And right off the bat, a lot of students are going to recognize that this is indeed an additive relationship. It seems that due to the fact that when we're multiplying a number with itself in sequence, if you were to append or place another 2 at the end of the stack, whatever you've multiplied 2 by currently, you would simply be adding an extra exponent that 2 would be raised to. So if, for example, you start with 2 to the 6, and you have another 2 that you multiply 2 to the 6 by, well, you've got a sequence of 2's that represents 2 to the 6, and I'm multiplying by a new 2. And of course, by the associative law, we could have just multiplied all of these guys together. And if we count up the number of 2's, you'll see that I now have 7 2's all multiplied in sequence. So we started with 2 to the 6, and if you attach or append another 2 to the end of 2 to the 6, then you get 2 to the 7th, thus verifying that indeed the exponents are more or less related to one another by this additive relationship, if you will. So we say that whenever a number is raised to power and it's multiplied by the same number raised to another power, we're going to add the exponent. So this is the exponent addition law. And this is really, really interesting because you could have something like x to the 15th power and you multiply it by x to the 7th power. And all you're going to do is you're going to add the exponents with each other. 15 and 7 is going to give you 22. Okay, and so now you have x to the 22. What's intriguing is that you could have something that's absolutely ridiculous. And in fact, this is what you often see on an ASVAB, is you'll have, say, some number raised to a ridiculous power like 105 multiplied by the same value raised to some other ridiculous number. And the trick here is just to remember that the relationship for exponents is additive. So you're going to take the exponents 105 and 325. You're going to go to the side of your page. You're going to add these together. 5 and 5 gives you 10, carry the 1. 1 and 2 is 3. 1 and 3 gives you 4. So now we have z to the 430th power. Fantastic. Let's keep playing around with exponents, shall we? But I want all students to put a star in their paper and write down the exponent addition law as part of their cheat sheet, as well as a number of examples of how to use the exponent addition law. Let's talk about the exponent product law, i.e., what happens if we took 2 to the 4th and, I don't know, raised it to the 3rd power, and we're like, what's going on here? What is this equal to? Well, starting with what's inside, 2 to the 4th, of course, would just be 2 times 2 times 2 times 2. But because you raise this quantity to the 3rd power, what you're doing is you're multiplying this stack of 2's with itself 3 times. So now we've got 2 times 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 2. And that means you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 2's that are multiplied by one another. Now, in mathematics, there is a simple technique for establishing relationships when it comes to these multiplicative properties, or when it comes to special algebraic theorems. And that is, in many instances, if we're trying to establish a relationship, you start with something that everybody can agree to. Everybody, for example, can probably agree that 2 to the fourth is the same thing as 2 multiplied with itself 4 times. And then further, a lot of students will agree that if you raise something to the third power, it means you need to take that something and multiply it by itself 3 times. And so even though it looks a little bit funny, 2 times 2 times 2 times 2 multiplied with 2 times 2 times 2 times 2 multiplied with 2 times 2 times 2 times 2 is really just applying this basic definition of raising something to the third power. And then, of course, we can remove the parentheses due to the associative law. We've talked about that a zillion times in class. So you can remove the parentheses, and then now you simply count up how many 2's you have. And at the end of the day, we should have 12 2's. So because we all agree on something very basic, now what we're going to do is we're going to increment a property inside of this expression in order to try to establish whether or not there exists a wider algebraic trend, shall we say. And so what I'm going to do is I'm going to focus in on this exponent 3, and I'm going to increment it by 1. We'll say we change that 3 to a 4. We're going to try to see or establish what happens here in order to determine whether there is a greater relationship, which of course there is. So when we increase 2 to the fourth and raise it to the fourth power, the only real difference is that now we've got 2 multiplied by itself in sequence 4 times. And at the end of the day, we should have 2 raised to the 16 power. There should be 16 2's that are all multiplied with each other if I did this correctly. So I've got 4 here, 4 here, 4 here, and looks like I added an extra 2. There we go. So there should be 16 2's altogether. And of course, I can keep going with this general idea. So if I take 2 to the 4 and I raise it to, say, the fifth power, you're going to now have 2 times 2 times 2 times 2 raised to the fifth. So you're going to get 2 times 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 2, which is going to give you 2 to the 20th. All right, just as before, we're going to try to establish a relationship within our exponents. So we said that 2 to the fourth raised to the third is the same thing as 2 to the 12th. 2 to the fourth raised to the fourth is equal to 2 to the 16th. And 2 to the fourth to the fifth is 2 to the 20th. And so now we're going to ask ourselves, how can I relate 4, 3, and 12, 4, 4, and 16, 4, 5, and 20? If I'm only using the rules addition, multiplication, subtraction, and division. If I'm only using these 4 rules, what goes inside of the box? And of course, in this instance, hope everyone would agree that what needs to go in the box has to be multiplication, because 4 times 3 gives you 12, 4 times 4 gives you 16, 4 times 5 gives you 20. And so we may say that for the exponent product rule, when you've got a number raised to a power, and then you go ahead and raise it to another power, the exponents multiply with each other. Next, we'll discuss the topic of the exponent distribution law, which is more or less an extension of the exponent product law. But I suppose before I get to that, I'll just give you an example of the exponent product law that's a little bit more involved than just raising something to one power and then raising it again. So for the exponent product rule, if you have a number, and let's just take the number x, because usually in these problem statements, they'll use an unknown number that they're going to exponentiate. And suppose we raise x to the third and then raise it to the fourth power. What's going to happen here is you're going to need to multiply the exponents together, and of course you get to the x to the 12th power as the result. Now, the interesting thing is that I could, if I'm trying to throw students off, raise something to a ridiculous power like 105, and then raise that to another power like 3, and students are going to have to know that this is the same thing as you just multiply 3 with 105. So you're going to have to go to the side of your paper, do 3 and 5. 3 times 5 gives you 15, carry 1. 3 and 0 is 0, plus 1 gives you 1. 3 and 1 is 3. So you get 315. So I've got z to the 315th power. Excellent. Now on to the exponent distribution law. So whenever you have two or more numbers and you raise it to a power, what happens is that each of these numbers effectively gets raised to a given power. And another fun fact is that this applies when numbers are straight out multiplying with each other. It also applies when you have one number divided by another number, because we know that division is just the same thing as multiplying by an inverse at this point. So it makes sense that if division is just multiplying with an inverse, if multiplication law follows this formula, then when you've got a number divided by another number, it follows a very similar idea. But we'll prove both. Are correct. And then finally, there is a final variety of the distribution law, and that is whenever you have, say, a number or a sequence of numbers that are raised to different powers. So like maybe you've got a first number that's raised to some value, a second number that's raised to a different value, and you raise that to a power, then each of these numbers gets raised to a power. And then what happens is that the exponents will multiply. Hence why we say it's analogous to the distribution law, because it's almost like you're distributing an exponent. It's not exactly the same thing, but it's close enough. So we'll use the vernacular distribution law just so that everybody's on board, on the same pages. So let's take something that is pretty basic again. And in order to prove this general principle, we're going to just take this and raise it to the second power and see what happens. Okay, if we took this and raised it to the second power, of course, you're multiplying a number by itself twice, just by the definition of exponentiation. And then due to the associative law, you can remove the parentheses. Due to the commutative law, you may move your numbers around a bit. So this is the associative law. You can remove the parentheses, and then when you start moving your terms, that's the commutative law. So now we've got 2 times 2 times x, or 2 quantity squared times x quantity squared. Now that's just a definition of exponentiation, meaning I've got two x's multiplied by one another, so I've got x squared, and I've got two sets of 2's multiplied by each other. So, we got 2x cubed. This will be 2x, 2x, and 2x. Remove your parentheses. You've got 2 cubed, x cubed, and that's just what we're left with. And finally, we'll do this for a fourth time. We've got 2x times itself 4 times. Again, just by definition of exponentiation. Remove your parentheses, because that's just what we're going to do. Move your numbers together. And then raise everything to a given exponent. All right, now we've got to establish the pattern. Right? We've got 2x quantity squared. That gave us 2 squared x squared. I've got 2x quantity cubed. That gives me 2 cubed x cubed. 2x quantity to the 4th power. That gave me 2 to the 4th x to the 4th power. And I hope that everybody can see that as a consequence, the exponents do indeed appear to distribute to each of the terms that exist inside of the sequence of parentheses, QED. Now the same phenomena happens for fractions. If you had, say, 2/3 and you raised it to the 3rd power, this would be 2 over 3 times 2 over 3 times 2 over 3. So the 2's are going to multiply across the top. The 3's would multiply across the bottom. And you'd get 2 to the 3rd and 3 to the 3rd. And so if you had 2/3 to the 4th power, this same pattern of things multiplying across the top would occur, except now you've got 4 2's and 4 3's that are multiplying with each other. So you get 2 to the 4th on top, 3 to the 4th on bottom, and finally you got 2 to the 2/3 raised to the 5th power. So you got 2/3, 2/3, 2/3, 2/3, 2/3. I hope everybody can see. Got a bunch of 2's, got a bunch of 3's. In conclusion, anytime you have one fraction or one number divided by another number raised to a power, or a fraction raised to a power, the numerator and the denominator both get raised to a specific power. Now let's look at how we may use these two rules in a more nuanced fashion. Suppose, of course, that I've got 105x y, and I decide to raise this to the 7th power, and I ask you, what is this going to be equal to? Well, of course, you could write out, 105xy times itself 7 times, and then, use the associative law, etc., etc. If you had simply remembered the distribution law of exponents, you may, however, simply say, all right, I've got the sequence of numbers. They're all multiplied together. They're raised to power. So I may take each of these values and simply raise them to a power. And the same is true if you've got something nutty, a little bit bonkers, like 2x over 7y raised to the 15th power. Like, don't burn yourself out on this too much. You're just going to take your numerator, raise it to a power, your denominator, raise it to a power, and voila, you're done. You may do it like that, or you could take your numerator and raise the whole chunk to the 15th power. The denominator raised the whole chunk to the 15th power. And from this, you obtain 2 to the 15th, x to the 15th, 7 to the 15th, y to the 15th. However you want to think about it. If you're distributing it to all of the values, or you're thinking about it like, of course, the numerator has to get raised to a specific power because that's how many times you'll have the quantities in the numerator multiplying in sequence. And similarly for the denominator would have to be raised to a given power due to, you have the denominator multiplied in sequence that many times. And so as a consequence, you then use the distribution law a second time to get 2 to the 15th, x to the 15th, 7 to the 15th, y to the 15th. And you're pretty much done. Okay, but note that there is, in fact, this last rule where you've got numbers raised to powers, and then you raise that to another power. And how does that work? Well, so this is kind of what happens whenever you've got a number that's pretty big, like 8. And 8 doesn't seem like a big number at all. But say we've got 8 and we've got x quantity squared. And what we're going to do is we're going to start off pretty basic, and we'll raise this to the second power. And we'll just see how this becomes a little bit complicated. So if we have 8x squared, then of course we've got 8x squared times 8x squared. If we just use the definition of exponentiation, we've got this quantity raised to the second power, so each of the terms needs to be multiplied by each other 2 times. So then using the associative law and then the commutative law, you can kind of group up your numbers with each other. And naturally, at this point, we may use the exponent addition law. The 2 and the 2 adds together. That gives you x to the 4th. The 8 times 8, of course, gives you 64. But we may say that just due to the definition of exponentiation, I've got 8 raised to the second power. Now, here's the deal. 2 to the third is actually equal to 8. And I may say that, not just because I've memorized this, but if you think about it, 2 to the third, of course, is 2 multiplied by itself 3 times. And 2 times 2 is 4, so we got 4 times 2, and 4 times 2 gives you 8. So what I really have written here when I've got this 8 raised to the second power is that this is actually 2 to the third raised to the second power. And similarly, if we back up a little bit, we've got this x squared times x squared, but we could just say that that's the same thing as x squared raised to the second power. So if we back up a little bit, and we've got this 8x squared quantity squared, then that is the same thing as 2 to the third power x squared quantity squared. And of course, that gives us 2 to the third power raised to the second, x to the second power raised to the second power. And this general pattern would happen regardless of the exponent that I raise my quantity to. So, if you had 8x squared raised to the third power, then you'd have 2 cubed x squared to the third, and that would give you 2 to the third raised to the third, x squared raised to the third, and so on and so forth. Whoops, I did to the third power, but I meant to say to the fourth power. There we go. Okay, cool beans. The last rule that we're going to learn about in this class is called the negative exponents. Okay, negative exponent. Negative exponents are a thing. And it turns out that whenever you have a number raised to a negative exponent, it's the same thing as writing that number inside of the denominator raised to a positive power, and vice versa. If you have a number that's in your denominator raised to an exponent that is negative, then it's the same thing as writing that value out as a regular number raised to a positive exponent. Now, how this arises is actually due to just the properties of division in general. And so, just for example, if you've got, let's say, we have to take a sufficiently large value, like 2 to the 5th. If you have 2 to the 5th and you divide it by 2, you ask yourself, what exactly happens here? Well, 2 to the 5th is the same thing as 2 multiplied by itself 5 times. And 2 to the first power is the same thing as just 2. Now, by the composite fraction rule, whenever you have a fraction, you may split the fraction open into the numerator being multiplied by a sequence of terms. And so we can go ahead and we can actually start separating out our numerator. So by the way, backing up to the rule of composite fractions, not only is this the case, but also if you have like 2 numbers, say, multiplied with each other, you can start breaking them up. So just note that c times a over b, for example, would give you c times a over b just as an extension to just the basic definition of the a over b rule. So now, the reason this is important is because what happens here is you've got 2 over 2. That would be this first quantity here. And this is going to be multiplied by 2 times 2 times 2 times 2. And of course, 2 divided by itself is just 1. So now you've got 1 times 2 times 2 times 2 times 2, or simply 2 to the 4th times 1. And 1 times anything is just that something, so you get 2 to the 4th. Now, if you keep increasing the exponent in the denominator, something interesting begins to happen. You can apply the trick that we did before. We've got 2 over 2 times 2 over 2 times 2 times 2 times 2. And of course, 2 over 2 just gives you 1. So we've got 1 times 1 times 2 times 2 times 2. And 1's just multiplied by itself. So that just gives you 1. 2 multiplied in sequence by itself 3 times gives you 2 cubed. And 2 cubed times 1 is just 2 cubed. Okay, are we starting to notice a pattern here when I increase the exponent in the denominator? And now I hope that I've made it clear what happens with these numbers in our denominator whenever they're divided by the same quantity in the numerator. So just to save some time, I'm going to just cross out terms that I have in common. When I write this 2 to the 5th, you'll see I have 5 2's multiplied together in the numerator. When I write out the 2 cubed, I've got 3 2's multiplied with each other. But because I've got a sequence of 2's that are dividing by one another, those are just going to cancel out for the same reasons above. I'll be left with 1 times 1 times 1 times 2 times 2, or simply 1 times 2 squared, or 2 squared. So the first thing that we start to notice, if we put our fractional terms together, or rather our exponents in the numerator divided by some value in the denominator, we try to establish a pattern, is that it seems the only way that we can establish a pattern between exponent values that are in the numerator and exponents in the denominator is if we say that it's almost like the exponents subtract from one another, meaning that because you have 2 to the first power, it's almost like when you had 2 to the 5th in the numerator, you subtracted 1 from the 5, giving you 2 to the 4th. When I had 2 to the 5th divided by 2 squared, of course, 5 minus 2 gives you 3. So it's almost like the exponents subtract when you have a raised to the m divided by a raised to the m. So we may write a new rule, and that is the exponent subtraction law. Okay, put a star in this. So just as an example, if you have 7 to the 15th power divided by 7 to the 10th, you may say this is the same thing as 7 to the 15 minus 10, or 7 to the 5th power. If you have 20 to the 5 divided by 20 to the 3rd, the exponents subtract, so 5 minus 3 gives you 2. I can say that this is 20 to the 2nd power with confidence. Okay, and of course, as a more complicated example, suppose you've got 5 to the 15th, x to the 3rd, divided by 5 to the 7th, x to the 2nd. You're going to essentially try to break this fraction up. It's going to give you 5 raised to the 15 minus 7 and x raised to the 3 minus 2. So you'll get 5 to the 8th power, x to the 1st, or simply 5 to the 8th, x. All right, so then the question obviously is, what does this have to do with negative exponents or with proving negative exponents? Well, as many students can probably surmise, if n is bigger than m, then you've got an issue because you'll be left with a negative exponent. And of course, the question is, what would happen? So let's consider just the simple case where you've got a number raised to power divided by the same number raised to the same power. What happens here? Well, in this case, you've got 2 times 2 times 2 times 2 times 2 all in sequence on the top, and you've got a sequence of 2's on the bottom. And so by breaking open the fractions like we did in our initial example, just to try to establish what in the world is going to happen, you've got a bunch of 2's divided by themselves. 2 divided by 2 gives you 1. So now we have a bunch of 1's, and 1 times 1 just gives you 1. So a sequence of 1's multiplied by themselves is just going to give you 1. But here's the deal. By the exponent subtraction law, you had 2 to the 5 minus 5 or 2 to the 0 power, and that gave you 1. So another interesting result that we're going to say in this particular lesson is the exponent 0 law. And that is to say, anytime you have a number raised to the 0 power, you always get 1. So go ahead and put that down in your notes. If you have 150x raised to the 0, that would be 150 to the 0 times x to the 0 due to the distribution law. And of course, 150 to the 0 power would be 1, and x to the 0 power would be 1. So you get 1 times 1 and just gives you 1. This is just an example of how to use the exponent 0 law. It's pretty nifty. Now, if I was to take 2 to the 5th over 2 to the 6th instead of 2 to the 5th, like in our previous example, then you've got the sequence of 2's all multiplied with each other and a sequence of 6's. But now you have 1 over 2 that will be remaining because all of the 2's in the numerator cancel out. That gives you 1. But there will be a remaining 2 in your denominator. So you'll be left with 1/2. And if you kept, say, increasing the exponent in your denominator, of course, you're going to have more 2's that remain. So your 2's cancel out, but now you've got 2 times 2, or 2 squared in the denominator. And if you just keep doing this, you get 2 to the 3rd in your denominator. And so in order to obtain the exponent, the negative exponent law, you just utilize your subtraction rule. So 2 to the 5th over 2 to the 6th, we know that's going to be 2 to the 5 minus 1 power, and that's going to give us -1. All right, 2 to the 5th over 2 to the 7th, that gives us 2 to the 5 minus 2, or 2 to the 5 minus 7, rather, which gives us 2 to the -2. And if I've got 2 to the 5th over 2 to the 8th, it's going to give me 2 to the 5 minus 8, or 2 to the -3rd power. And voila, we just line up our terms to see what happens. Where I'm getting this 1 over 2 cubed was from this initial line, 2 to the 5th divided by 2 to the 8th. So we said 2 to the 5th divided by 2 to the 8th gives you 2 raised to the -3rd power, the subtraction rule. But then also we may say that 2 to the -3rd power is equal to 1 over 2 cubed. And where I'm getting this 1 over 2 squared is that we said that 2 to the 5th divided by 2 to the 7th was the same thing as 2 to the -2. And so I've got 2 to the -2, and that is apparently the same thing as 1 over 2 squared. And the same would be true with 2 raised to the -1 power. That gave me just this singular 2 in the denominator, which of course we may write as 1 over 2 to the first power as a definition of exponentiation. And so I hope I've established in the students' minds that whenever you have a negative exponent, all you're going to do is you're going to flip it into the denominator of a fraction. Now, it's actually easier to prove what happens if you have a negative exponent in your denominator. In order to demonstrate what occurs here, consider taking a fraction such as 1 over 2 to the -3rd power, okay? And what's going to occur is that you've got 2 to the -3rd power in your denominator, and we said that 2 to the -3rd was the same thing as 1 over 2 cubed. So now I've got a fraction divided by a fraction. We all know that we need to flip and multiply. And so I've got 1 times 2 cubed, or 2 cubed over 1, and anything divided by 1 is just that something. If I had 1 over 2 to the -4th power, that would be very similarly 1 over 2 to the 4th. Sorry, 1 over 2 to the 4th, and that would be 1 times 2 to the 4 over 1 by the fraction division rule, and then that would just give me 2 to the 4th over 1, which gives me 2 to the 4th. And of course, we can do this however many times I want to do it. So, in conclusion, if you've got 1 over a number raised to a negative power, that's the same thing as 1 over the number raised to a positive power, which is 1 times number raised to positive power over 1, which just gives you the number raised to a positive power, and you are finished. That is all we're going to do in this particular chapter, guys. I will see you in class. Take care.